heard the title, I'm here. I want to acknowledge my co-authors and other people who have worked on this work. We're all part of our WPI, WE research group. There's faculty and PhD students, and I wanted to point out the kite-powered water pump you see today. It was designed and built and tested fully by in undergraduate student projects. We've had almost 50 undergraduate students working on this since 2007. Another consultant on our group is Dr. Jitendra Goela. Just wanted to point out, he did work on kite-powered systems back in the late 70s, early 80s, sort of the Lloyd time frame, and he's often not remembered anymore, but find his papers. He was talking about a lot of the issues we still talk about today. We have NSF funding, especially on the research side, and some other partners and so forth. So, our overall project goals at WPI, and in the red is what we'll talk about largely today. Again, we want to show you the design and development of a low-cost, kite-powered water pump, and we'll see what low cost means. But this is meant for developing nations, and again, we've done those in the projects. We'll show you design of this system, some dynamic modeling, and also some videos, some field testing. More on the research side of WPI. We've started to work on development of computational fluid dynamics simulations and Navier scope solvers for the entire flow field. I just wanted to show you some preliminary results there. We also do kite control studies, path optimization and things, but we're not talking about those today. So, our overall goal here, again, we want to design a low-cost AWE system for use in developing nations to alleviate water shortages. You know, this is a big problem, of course, we often forget about. Over 500 million people worldwide lack access to safe water right now, for drinking, for hygiene, and so forth. Over 4 million preventable deaths per year from this problem. And things we don't think about in the developed world, that children carrying water, children who have to carry water all day to serve their families can't attend school, for example, so it affects education. So we got into this a few years ago, wanted to see if the AWE world could start to affect this. So our design goals for this water pump, again, a lower cost AWE alternative to water pumping windmills. Again, we're all competing with wind turbines, right? But in this smaller scale world, we're really competing with these windmills. Now these, of course, have never been optimized too well, so we should be able to compete with them well.
Can we have any help?
Yeah.
Somebody who's knowledgeable about the system here? So it's we continue with this system.
Okay. So what does low cost mean? We have a design goal for the system. It's very low cost, less than $2,500 for capital costs. We want to build something workable with that. This would exclude well drilling and water storage, because those would be common to wind turbines also. All right. So in the end, you're going to see it's really the design challenge is to develop simple, low-cost solutions for kite control and other kite aspects. You know, we can't have complex automatic control systems. We need, if anything, just simple, what I call passive kite control. Let's see what that might mean. So here is the system then, and talk you through it a little bit. It is, it's not a pumping system. It's a bit different. It is based on a rocking arm. So here's a rocking arm with a pivot and an A-frame. All right. The kite aerodynamic angle of attack control is down here. We'll talk about the details, how it works later. But these are just drawn in. But we do have two kite tethers, one to a trailing edge, the power line, so to speak, one to the leading edge, the power, one to the trailing edge, the AOA control. All right. And then, it does become It's a big lever arm here. You see the rocking arm goes up and down, attached to a linkage to just a standard hand water pump. So these are hand water pumps, very low cost, $200 that are already used in developing nations. And of course, an outlet for the water. We'll talk about some other details there. All right. So, I mean, here's a schematic of the system. Again, it's pretty simple. You know, during a pumping phase, if we have large lift on the kite and the kite is moving up, of course the arm moves up, again, transferred through the linkage. This is a simple displacement or lift pump, driving upwards with a valve closed down here, and we pump water out. To bring the arm down, we stall the kite, all right, lower lift forces stall the kite, and create a periodic motion. Very simple operation. A nice feature of this, to show you, if we remove one linkage here, simply remove one linkage, and now it can operate. It can operate with hand operation by a human operator. All right. So we think this is going to be important for implementation. When the wind dies, if the wind dies, we don't want to leave people without water. Remove the linkage. They can still, again, we're talking people with subsistence living here. They can still be pumping, have a well and have the hand water pump to use them. All right. So that's the basic operation. Again, some of the details, the key features. We use a sled kite of about 8 meters squared. This is a very stable kite, and that's what helps us eliminate no complex electronic kite control. Really, you put this up here, and as long as the wind is blowing, it'll stay in the kite, stay in the air for really hours without any input. Some of the tether details, they're really off-the-shelf tethers. The water pump is used heavily in the developing world. It's a juice model, all right. And again, you see some of the details there. We do have a head simulation valve here, all right. This is meant to simulate deeper wells for laboratory and field testing. You see we're on a beach here, actually, in New Hampshire, USA, and people don't like you digging a 50-foot well, right? So we dig like a 4-foot well, put a bucket down there, and simulate higher pressure drops, deeper wells with it's essentially an adjustable orifice. And we did meet our design goal. What you saw was built at least material and fabrication costs for about $2,300. All right, I will show videos of this operating, but I wanted to show some modeling first, modeling we did first to see if this could work and what it might predict. So a lot of details here. I'm just going to hit the highlights. But we do have a MATLAB-based model. It's ODEs. Here are tether dynamics, all the details, but we do account for tether, lift, drag, and weight forces. Here are rocking arm dynamics through that linkage. We have kinematic and kinetic linkage models. We have a simple pump model. We're not getting those details today. And we have linear, quasi-static, really, aerodynamic models for the kite. We do have a non-straight tether. All right, we account for the lift and drag on the tether shape. So here are 4 more ODs that are solved, and the details are in. We do have in the AWE textbook. We have a whole chapter on that, and you could see the details later. You'll see some non-straight tether shapes that we do account for. All right, for this model, just a baseline simulation. We did run this to match the proposed water pump geometry, the right kite area, that's our kite weight. Say we model at a wind speed of 6 meters per second. We vary all of these. You'll see here's a typical case. In later videos, we don't fly that high, but we did simulate it that here. All right. Here's typical simulation results. Arm angle over everything versus time here. You see we predict the periodic motion of the arm with a frequency of about a cycle about every 4 seconds. Tether tensions, we picked our tether based on those. You get these peaks of maybe 1,400 newtons. Here we're at about 500 newtons. So 100-pound forces on these tethers, usual. Here's the volume pump versus time, and we'll see more results on that. Here is the kite motion. I mentioned this it's a very stable kite, and largely we don't have crosswind motions, by the way. That reduces our power, but we have enough power for our system. So you see a kite motion, a pumping phase and a return phase in a 2D plane here with not a lot of crosswind motion. Here's the tether shapes I mentioned, going from zero tether drag, adding tether drag with bigger tethers, we get some non-straight shifts. All right, and for some of the key ideas. We did some design studies. Here is pumping rate, which is predicted, now versus tether length versus tether diameter. And we do see these fall-offs. If tether length gets too high, diameter gets too high, our tether drag takes over. So we have a sweet spot, so to speak, kind of similar for yo-yo and pumping, above about 400 meters is the one I'll focus on. Tether length over about 400 meters. We get a degradation in the pumping rate, and that's because a nice periodic kite trajectory turns into this. You see the drag of the tether starts to degrade things. We drift downstream and eventually fall to lower altitudes. All right, so that was a nice prediction and some design limits, if you will. Here's a standard pumping rate versus well depth curve. And we do follow expected trends with well depth, and these are different wind speeds. You look here, maybe at a wind speed of 6 meters per second. We predict a pumping rate of 8,000 liters per day. That would meet the water needs of about 400 people per day. All right, developing nation, you're talking about 20 liters per day per person. All right, so that's some of the modeling. Then to the field testing, to some actual videos of this operating, but I want that angle of attack control a little bit more on that. We do have a trailing edge tether come up. It does split in two, and this is where a lot of our work has been in the last year or so. We've tried several angle of attack control devices, and again, they have to be very simple. Call these design 1, 2, and 3. I'll mention them later when you see videos. But here's some animations. This would be the rocking arm, the end of the rocking arm in the up position. Here's the power tether, here's the trailing edge tether. This idea was a simple sliding weight. It's pretty elegant. Arm goes up, weight slides down, pulls on the trailing edge tether, and you stall the kite. Here we found the weight couldn't overcome the kite force during the stall. For this to work, this weight had to get large, and then the arm wouldn't go up, for example. So things are coupled together. So we tried some other things. How about let's force that weight to move. You see here I add another tether simple just to the ground, and this forces the weight to move independent of the weight. And here's the first video. Now we're manually operating this. The kite isn't doing it just for demonstration purposes, but you see kite pulls it up. The weight starts to move. There you're in a power phase. Kite pulls it up. Pull on the trailing edge tether. Kite stalls, and arm will come down. All right. That's design 2, let's say, and that's still a viable option. We're still studying it. At times, this doesn't work that well in light winds, maybe down to 3 or 4 meters per second, because this whole device gets a bit heavy for the arm. A design 3 will show you also. We noticed that once you look at this design for a while, notice the trailing edge tether, it really does come down to the ground. It just goes through that weight. Well, why not then attach the trailing edge tether, that would be this one, directly to the ground, get rid of the weight, the sliding weight, and all of this. And that's what we're currently studying here, the relative position of the trailing and leading edge tether to stall the kite. When the arm goes up, you're effectively lengthening or pulling on the trailing edge to stall the kite. All right, so design 2, design 3 there are both possible. And then here we go, some field testing videos. All right. Here we're on a local farm near our campus, that I'll talk about more later. This is just going to be a kite launch, but this is the design 3. The trailing edge tether, you might see it, is right to the ground. The leading edge tether is to the end of the arm. Up goes the kite. It's not a real strong wind day, but up it goes. The arm will eventually raise in the next video.
What is that attached to the kite? at the end?
Oh, that's the tail of the stability tail. All right, tail to help for stability. Now here we are on that beach again, and here's the system in operation. It's that design 2. All right, and we're getting pretty good cycle rate and pretty good pumping. Wind speed's about 6 meters per second, as I said here. We'll go in and show you the water coming out. Okay. So we're pumping away. And we'll go up and see the kite. Again, it is the sled kite. Alright. So that was 1, that design 2 option. Oh. Sorry about that, I don't know what's going on.
Is living.
Take a question or two.
Yes.
There are any questions.
I have a question.
Sure.
How long does it take to fill the bucket?
We'll show you, we pump at a rate of like 150 liters per day. So you gotta work back. But a minute or so, you have to fill up the bucket. Yeah, it's not.
The computer seems to be there.
Oh, no.
Yeah.
How much energy does the system need for control?
What's that?
How much energy does the system, like electricity, does it?
There's no,
I thought
the sliding weight's all you saw. There's no electrical components or electricity drain that way. Must be a plug. There, the videos don't run well. That's why I'm here. You think that after? We can try it. You did put it on there. Yeah. Yes. Yeah. Okay, we're back on the other computer. Here's another video I wanted to show you in kite motion. Here's it is stalling now. Return arm going down. We power and go up, a nice stall there. Sometimes some crosswind motion that increases the force a bit. Okay, and then a bit more of this design 3 testing. A question up here, you know, our best operation, we get about 5 cycles per minute, about 150 liters of our pumping rate. But I did want to show you, you know, where we are. The pump operates well within a fairly narrow wind window, around 6 meters per second. All right. You were showing a lower wind, seeing a lower wind speed there, and you might have seen arm did at times have some trouble coming up. All right. And there'll be a later, here'll be a higher wind situation. The wind's maybe 14 meters per second or so. The arm, although oscillating at times, does stick up. So we are working, this is what, working to achieve better kite stall and handling of wind variability to reduce this pump downtime, as we would call it. All right. With that, we should get higher pumping rates. Okay, so that's the kind of power pump side of things. Having used up time, I'll go more quickly, but I did just want to show you on our research side, we are doing CFD simulations of AWE. This means, for now, two-dimensional Navier-Stokes solution for the entire flow field. We want to do a basic pumping system. I'll leave the numerical methods for some questions afterwards, but based on immersed boundary methods, E&O schemes, we have simple springs between our kite elements and also elastic tethers, and just show you now this is a kite, and you could consider this a bridle with say there's a kite control unit right there, so we're only doing the near flow field near the kite, but we are doing a pumping power and retraction phase, killing the angle of attack as you see there. Maybe one more time. All right, and again, it was on there. Our goal is to improve, now linear quasi-static aerodynamic models. If there's more we can learn from the CFD work, and of course there's plenty of CFD challenges along the way. From the CFD simulation results, we see these step changes, right? Step changes in the angle of attack, in the tether force in the red here, and we have shown net power output with this CFD code, positive output during a power phase compared to a return phase, for example. All right, but in 2D for right now. So the main part of our talk, we have this working low-cost kite-powered water pump, built and tested now. We've been through, basic operations established. We still do need to refine things. And there's the CFD work. For future work, we do need more extensive field testing. The video used to show in the grass. We are now semi-permanently installed at a local Heifer International heifer farm in Massachusetts. And in fact, early October, we're going to have our first public demonstration of this system at an open house day that they have. As we said, we have to refine to eliminate the pump downtime. And the eventual goal, WPI has a nice global program. We send a lot of engineering students overseas, for example, to Namibia, to some developing nations. And that should ease our implementation to, in the next 3 years or so, hopefully put it into a developing nation. And the CFD simulations, again, we've started these. They're fairly preliminary. We need larger kite elevation changes to have, I didn't point out, the amount our kite moves, it moves, for now we've modeled this pumping arm system. It moves a couple chord lengths like our pumping arm system, but we want to have a true yo-yo or pumping system where it has greater elevation changes. That may take moving grids, and eventually we want to move into 3D, where you now be, as others have started to show, modeling 3D elastic surfaces. This is just work on parachutes in parallel is doing some similar things, and we can build off of those. All right, sorry for the technical difficulties. But per day.
Yeah, 24 hours. You said you're only doing 150 meters an hour. So
Yeah, we're not. There's the model. Yeah, we're not there yet. Right. But that's the pump downtime I tried to show you. If we could pump all the time at that rate of about 6 to 8 cycles per minute, as we
So you consider designs where you're actually pulling for a longer period of time and then translating that into the ground rather
saving in a, yeah,
Rather than having a rock for it.
yeah, saving in a flywheel and things.
Yeah.
Yeah, we've looked at some things like that. No time today, but we've also done an electrical generation version of this, which would eliminate do some of that kind of thing. So, yeah.
There was one little bit.
I don't understand how do you ensure that the system is not reaching an equilibrium point? It's always cycling, but it could. I mean, in one position it's powering, and in the other one it's depowering.
Right.
It's not reaching a kind of equilibrium point.
Yeah, I mean, we haven't seen that in our testing. The model with, there is a counterweight. You take it out, there's a counterweight on the end of the arm that's meant to bring it down. The modeling shows that will work with the proper counterweight. But you're talking, we may be in some of the downtime, we may be seeing, and that's where we need refinement.
There was an earlier question.
Yeah, I wanted to ask, how is it compared to the traditional way of wind turbine kind of pump system?
Right. Yeah, the cost comparison.
Yeah, exactly.
It'd be at least double for a typical windmill like that. And you can imagine, we've talked about material costs per here it would be per volume pump, but those towers are very complex and parts, so we're doing the same things we're trying to do in larger scales to reduce those costs. And we've cut it in half, we believe.
Which model then you mean, I presume? With the assumption that the model would be correct?
Yeah.
Okay.
I guess for the intended, purpose, so should be maintenance free almost and easy to use.
Yeah, I mean, it's maintenance, it's some of the same issues that are in any AWE system. Kite, how long does the kite last, right? Of course, tether degradation, things like that. The rest of it's pretty robust and based on a water pump that's been out there forever. So.
There was a final question.
Do you have a scenario to pump water to houses, or is it just planned to?
Jen, in these situations, usually like central for a town, a village with a water storage tank would be the first application. Now it might be in a developed nation, off grid, somebody off grid in the wilds of Maine or somewhere, right? May use it directly to a house,
Because I was thinking about the water hack that you have to overcome.
That's.
So,
I mean, we've
it's
done
just
that.
for
That's just
a
an
few
additional
meters.
pressure drop.
It's just a few meters.
Yeah, up to say a storage tank or, that definitely. We've done testing where we put it through a long 500-foot hose to add that pressure drop. It's worked just fine. So that's doable.
Thank you again.
Yeah.